Hi everyone, so we're going to finish off the last part of chapter 15. So everything that we've done so far in the last couple of videos, in the last couple of lectures, has been looking at, from the point of the equilibrium constant, where everything's already at equilibrium, right? We're asking what are going to be the equilibrium concentrations. What we're going to explore here is what happens if you have a balanced chemical reaction. Maybe we had, like we had last time, which was, oops, wrong thing, right? When we had our hydrogen and our iodine reacting in equilibrium to form HI, right? What if we didn't have equilibrium concentrations of H2, I2, or HI, right? We need to ask the question, well, given the concentrations that I do have, would I predict that the reaction would move forward, so from reactants to products? Or, based on the concentrations do I have, would that indicate that the reaction is going to go in reverse, right? So how do we quantify that? And we quantify it with the variable Q, which is going to be our equilibrium reaction quotient. So K is our constant, and Q is our quotient. And so I'm just going to give you these definitions now, but we're going to see it makes a lot more sense when you put them into play. So we got three different scenarios. One where QC will be less than KC. And we're going to see under those conditions, reactants are going to go towards products. So that means the forward reaction is favored when QC is less than KC. If QC is greater than KC, the products are going to go to the reactants. And what does that mean? Well, it means the reverse reaction is going to happen. And if QC equals KC, then at that point there's going to be no net reaction. So effectively it says it's already at equilibrium. So what is this Q, right? It's actually, you don't have to learn any new equation. All it is if I have a reaction quotient, it's the exact same equation as KC, where it's the concentration of the products raised to some power over the concentration of the reactants. Again, raised to some power. Just like we've seen for K, for the equilibrium constant, the only difference is these concentrations are not necessarily equilibrium concentrations. And I can't spell, but you can know what I'm saying. Necessarily, or not necessarily equilibrium concentration. So we're going to see what we can do with that, and then why, why when QC is less than KC, why does that explain that it goes forward? And when it's bigger than KC, why does it go in reverse? Oops, let me try to get to the next slide. There we go. All right, so let's take for an example, again, if we have that reaction, H2 gas plus I2 gas in equilibrium with 2HI. So just for practice, we know that if I wrote out the equilibrium constant expression, right, it's going to be my products, which is the concentration of HI squared over the concentration of H2 multiplied by the concentration of I2. I'm going to be specific here. I'm going to put in a subscript that specifically when we're dealing with K, we're dealing with equilibrium concentrations. Q, on the other hand, we said is the exact same expression, sorry for that, exact same expression. The only difference is, it's not necessarily at equilibrium, right? So let's take a look. On the first one we had, when QC was less than KC. Well, what does that mean? Well, if we think about a number as a fraction, the only way I can make this number Q less than this number KC, so if this is my constant and I can't change that, that's why I'm comparing Q directly to it. So if Q is less than KC, the only way that it can happen is if the denominator is too big, right? So it's the idea of having 1/2 versus 1/4. The bigger denominator of 1/4 is actually making the whole number smaller. And that's what we're seeing here. So what does that tell me? Well, if my denominator is too big, that means my concentration of my reactants are too much. And so what that's going to tell me is to approach equilibrium, I'm going to take those reactants, run the reaction forward to create more products. Eventually, the concentration of products and reactants will be at their equilibrium concentrations, and then at that point, we'll be under those conditions where K equals Q. So I know that can be a little bit confusing, seeing, trying to rationalize, well, is the denominator bigger, is the numerator bigger, does it tell you if it goes backwards or forwards? I have a little trick that I use to help me figure out if a reaction is going to go forward or in the reverse reaction. So let's keep sticking with this idea of QC less than KC. So what I'm going to do is I'm going to just draw a little diagram. And I'm going to call this value down here KC. And actually, this is Gibbs energy that we're plotting, though we don't really actually need to know that. That's fine, you don't have to label it. This is more just like a visual that will help you figure out, does my reaction go forward or reverse? So if my QC is less than KC, I'm going to put it somewhere on this graph, right? It's somewhere up here. But if I think of this as a potential well, so imagine this is like a ball sitting on a hill, well, which way is the ball going to roll? It's going to roll down the hill and specifically to the right. Reactants to products. So it helps visualize. If you do a little quick sketch, QC less than KC, well, it's going to roll to the right. Reactants will then go to products. Don't have to overthink it. We can also apply the same logic for the condition where QC is greater than KC. So we could just memorize that the reverse reaction is going to be dominant, or in case we forget, we can always just sketch real quick. So at the bottom of my hill is always KC. Well, QC is now bigger. I'm on this side of KC. So where's it going to go? It's going to roll back and down to the left. So in that case, the reverse reaction is dominant, and products will then be converted into reactants. So there's a couple different ways we can look at it, but effectively the take-home message that I want you to get for Q is that the expression is the exact same as that for KC. The only difference is that they're not necessarily at equilibrium concentrations. And then if you don't have to do it this way, but I find it the best way. Getting comfortable using this quick little sketch to figure if the reverse reaction or the forward reaction will dominate. So basically this is just another figure that I had basically saying the same thing. If you want to think of it this way, that way it works as well. It's basically just another way to visualize that that curve that I was showing you in the last example. So, I think you might have heard me say this phrase before, but we're going to introduce, and this is going to be the last part of Chapter 15, it's taking the idea of QC, and instead of just being an abstract number, what is it actually telling us that's physically happening? And that's going to be Le Chatelier's principle. And we'll read through it like we always do, and then we'll break it apart. So it says, if a stress is applied to a reaction mixture at equilibrium, then the net reaction occurs in the direction that relieves the stress. So what is an example of a stress on the system? Well, I could change the concentration of some of the reactants or products. We know that would immediately change QC, which then is going to, quote-unquote, stress the system, and the system will try to get back to equilibrium. We're going to find out that we can change variables like pressure, temperature, and volume. So effectively, what you're looking at, honestly, PV equals nRT. These are the type of things that we can change to stress out a system that's at equilibrium. And so that's what we have here. And we'll look at them in this order. Changes in concentration, pressure and volume changes, and then we'll finally look at temperature changes. So there's a lot of words on the screen. It's mostly there so you have it for your notes. We'll do some examples sketching what's happening. But let's read through it, and then I'll give you another visual device that you can use to basically quickly figure out these types of problems. So it says, in general, when equilibrium is disturbed by the addition or removal of any reactant or products, Le Chatelier's principle is going to make the following prediction. The concentration stress, if I'm adding a reactant or a product, is going to be relieved by net reaction in the direction that consumes the added substance. So I think I might have a blank slide after this. Great. No, I don't. Darn it. So what I'm going to do, I can just show you really quick. I'll do it in the margin. Right, we have, let's take our other reaction that we used to have. Actually, we can just do, well, actually, let's stick with something that's real. So again, I'll go back to that reaction. We've used a lot now, right? So when I'm thinking about if something is in equilibrium, I think of like a seesaw. That's telling me that my reactants and products, whatever those concentrations are, they're at equilibrium. So we're balanced on the seesaw. So if I say added more of the products, so HI, so I've stressed the system by adding something, what is that going to do? Think about what happens on a seesaw. If you add stuff to one side, well, now the products are too heavy, and so it's going to sink to one side. Well, how do I get back to being at equilibrium, having a balanced seesaw? The products have to be converted back into reactants until a new equilibrium is established. And again, I will have a balanced seesaw. We can do the same thing. What happens instead of adding more product, which is unusual? You know, it may be more common to add more reactant. Maybe I add more H2. In that case, right, we can sketch what would happen to our system that was already in equilibrium. There's too many reactants now, and it's going to have to run forward, consuming those reactants to make more products, again, until I get back to a seesaw that's at equilibrium. The other way you can look at it, instead of adding things, is to subtract reactants or products. And this is actually really common to do, especially in organic chemistry. What you tend to do is you pull off product as it's formed. So it's artificially keeping everything low on this side, so below equilibrium, which then drives the reaction forward. So it's a common technique. Oops, let me get rid of it. Made it a mess. Equilibrium with 2HI. So what happens if we look at a removal? It's the same idea. Let's start at equilibrium and imagine I do that technique where I can pull off some of the product. We got to stop and think what would happen in real life. Well, what happens if I took weight off of the product side? What's going to end up happening is, because now that it's lighter, my seesaw is going to look like this. Well, which way is the seesaw going to try to get back into equilibrium? Again, it's going to try to go and alleviate that stress. So by removing product, I've actually forced the reaction to keep moving forward. And then I think you've picked up on this point now. You can do the same exercise with removing one of the reactants and then seeing what would happen to equilibrium then. So this is just a summary slide. I don't think it's worth it to memorize, though if you find it more comfortable to do that, that's fine. For me, I still find having a sketch like this much more easy to follow. But it's up to you, however, whatever works for you. So let's see what this would look like, kind of just graphed out. So I've taken this reaction where nitrogen is going to be reduced by hydrogen to form ammonia. So we're going to start at some initial equilibrium concentration, and this is what we see here. And by definition of equilibrium, QC equals KC. So then what I do is I stress the system. I've added more N2, and that's what you can see down here in the purple. I added, so it spikes it in. That is the stress on the system. Ways the stress is going to relieve itself. Well, if I sketch my seesaw, I added too many reactants now. So I can predict that my reaction is going to go from reactants to products, and that's exactly what we see. What we see is that if we're predicting the forward reaction, that means H2 must be consumed because it's a reactant, and N2 will be consumed because it's a reactant. It's exactly what we see. And the same thing happens here. Because we're running the reaction forward, you're going to predict to make more product. And eventually what you're going to get to is a new equilibrium, and once that equilibrium is established, nothing's going to change until you stress the system again. So let's do this really quickly. I don't want to spend too much time on this. I've already got it worked out on the screen, so I'm not going to write through it, because it's mostly just plugging things into the correct expression, either KC or QC. So let's read through this, and then I have the math typed up on the next slide. So we have this reaction, and it's given me a temperature at which the reaction occurs at. We've seen that before. We have to specify the temperature because KC is dependent on temperature. There's my KC for the reaction. It says I have an equilibrium mixture where I have my N2 concentration, my H2 concentration, and my ammonia concentration. Then what I'm doing is I'm stressing the system or disturbing it by increasing the amount of N2. Originally, oh, I messed that up. That was a typo. Originally, this was supposed to be 0.50. But I've increased the concentration to 1.5. And so this is what I would do, right? I have that information that's telling me, okay, here's my concentration of N2, H2, and then my ammonia. I know it's not in equilibrium because I've disturbed the system, so I can throw it into my Q expression, solve for Q. You'll get a value for Q. You can directly compare it to the value for Kc because that's not changing. If we'd forgotten what does it mean when QC is less than Kc, again, I can do that quick sketch. QC being less than Kc, I'm going to predict that the reaction is going to go forward. And it's exactly what we see. And we saw that in the last slide too, when I graphed things. But since QC is less than Kc, reactants will be consumed, and the reaction will move from the left to the right. So that's going to finish up talking about changes in concentration. So now what we're looking at is changes in pressure and volume. And actually, we're going to treat them as one idea. The reason for that is because as volume decreases, pressure goes up. Because you can think about that like putting pressure on a balloon. When you decrease its volume by crushing it, the pressure on the inside increases until the balloon explodes, right? So let's think about what's happening. So we'll read through this, and then I have an example on the next slide. So it says, in general, when equilibrium is disturbed by a change in volume, which results in a corresponding change in the pressure. It's saying Le Chatelier's principle is going to predict, right, an increase in pressure by reducing the volume. So that's the only way we're going to change pressure here. We're not pumping more gas in, because that would be like adding more moles of gas. It'd be like the last slides we did with changing concentration. Now I'm going to reduce the volume. So it's like taking something that used to be, say, oops, why doesn't it let me write on the screen? Right? Something that used to be 2 liters, and then you crush it down to 1 liter. Well, that pressure's going up. You have the same amount of stuff, now a smaller space. So I'm increasing the pressure by reducing the volume. And what it's going to do is bring about a net reaction in the direction that decreases the number of moles of gas. So when the pressure goes up, right, the volume is going to be constant. The way the reaction tries to compensate for this change in disturbing equilibrium is to get rid of as many moles of gas as possible. So it'll try to go towards the side of the reactant that has less moles of gas. And we'll do an example in the next slide so you'll see exactly what I mean. But let's just finish reading off the definitions. If we bring about a decrease in pressure, so it's like doing the opposite, starting at 1 liter and then going to 2, by expanding the volume, right? What that's going to do is it stresses the system, and the net reaction is going to move in the direction that increases the number of moles of gas. So let's see an example here. So we have the same reaction we've been looking at for all of these, which is by nitrogen being reduced by hydrogen to make ammonia. So it's telling me I have a Kc, I'm giving a temperature at which it happens at, and I'm told the equilibrium mixture started at 1.5 molar nitrogen, 3 moles of hydrogen, and 1.98 molar ammonia. It's telling me that I've reduced the volume by a factor of 2. Effectively, it means if I was at 1 liter, now I'm at a half a liter, is what I've done. So if we think about that, if we have some container that has gas in it, right? We'll have something that can describe it as, PV equals nRT, right? So what I've done now, I've reduced the volume twofold. So I've basically have the same number of particles, but now jammed into a smaller box, right? So if I look at this, if I try to rearrange PV equals nRT, if I do it as N over V equals P over RT, well, RT is going to be constant because R is a constant and I can't change temperature because if I change the temperature, I change the K. So what I'm seeing is so if this is concentration, the only way to alleviate changes in concentration is going to be by changes in pressure. So in this way, pressure and concentration, we're still dealing with the same, almost with the same idea of what we were doing when we were looking at changes in number of moles. So that was a lot of talking. Let me show you what I mean with math. So by decreasing that volume by twofold, what we've done is effectively doubled all the concentrations. So that's what I have down here. So there's my concentration of ammonia that's been doubled, so 1.98 times 2. I messed up. Again, sorry guys with the typo. This should actually have been 0.75. I guess I went back and screwed with things and then didn't update it. Right, so we have 0.75. There's my doubled concentration for N2. And then for the concentration of H2, I've doubled that as well. So I go through, plug everything in, you're just solving for a value for Q. We see that Q is less than Kc, and again, we do our little sketch, Q less than Kc, we know we're going to roll downhill and to the right. What does the right mean? It means the forward reaction will dominate. It's exactly what we're seeing here. It's going to move from left to right. All right, and then the last thing we're going to talk about is how temperature, well, second to last thing, we're going to talk about catalysis for one slide at the end, but talking about temperature's effect on equilibrium. So it gets pretty complicated. We're not going to go too deep into it, but I just want to remind you, if we go back to the Arrhenius equation, that looks like this, where we can see that the rate constant is definitely affected by temperature. It's weird to see when it's in the exponent, but effectively what it's saying is temperature goes up, K goes up. And we also know that another way for the equilibrium expression constant is K forward over K reverse. So we can see a direct link, because both K's will have different equations, but they're both linked to temperature. So we have this link, temperature affects K, K affects big K. So we do know that, actually, unlike with the other examples, when we were changing the variables, like stressing the system by adding stuff, taking away stuff, changing the pressure or volume, we were directly looking at changes in Q. Now that we see that K is dependent upon T, when we change temperature, we're actually changing Q itself. Oh, sorry, changing K itself with temperature changes. So it's kind of a cheater way to do it, but it actually works really well. Let me see if I have a blank slide after this. I thought I did. Nope, I don't. I'll just do it here. So really quickly, what we can look at is kind of a cheater way to figure this one out. Oops, sorry, I'm trying to get the writing tool to work. If we go back and we treat, I'm going to rewrite it. Oops, why did it keep doing that? Come on. Alright, sorry for that. I'm just going to rewrite that equation, but I'm going to include one additional addition. It's kind of redundant. We can see that the delta H is negative. Well, that means it's going to be exothermic, so it means the reaction happens and then heat's released. I'm going to write that as a reactant. So I'm going to have heat on the product side because it's being released. What we're going to do is we can pretend like heat is a reactant. It's not real, it doesn't explain physically what's happening, but it's a good stand-in to help us figure out what direction a reaction will go in. So if we actually look here and make this prediction, there's my reactants and products. If I heat this reaction up, so temperature goes up, it's actually counterintuitive. For exothermic reactions, that's like increasing the amount of products I have. Exothermic reactions are going to run in reverse when you heat them up. Because what you're looking like here, if I added more heat, well, it's like adding like heavier products over here. So the only way to alleviate that stress is to run the reaction in reverse. And that's what we're actually going to see, is that for exothermic reactions, heating them actually causes the reverse reaction to be favored. And we can see that we can apply the same idea to an endothermic reaction too. And so basically this is what these words are saying, summarizing. It's basically saying for exothermic reactions, right? A decrease, so the K itself actually decreases as the temperature increases. That is the real reason why it gets a little bit more complicated. We can also just, actually, let's not get that deep into it. I just want to keep, let's stick with what we need to know. So we know that K is being directly changed, but like I said in that last example, we can treat heat as a product or a reactant, and we can just go back to our regular seesaw example. And it's the same thing we'll see here. Endothermic reactions, when you increase the K itself will increase as the temperature increases. What does that effectively tell me? If I have reactants to products and I have an endothermic reaction, so heat is being consumed during the reaction, so it feels cold. Well, if I increase the temperature, that's like having more reactants, because there's my heat, so the reaction will go forward. So when you heat endothermic reactions, the forward reaction is going to be favored. And so this is going to be the last slide. I probably should have deleted this one, because I'll use it as a teaching moment. So, we've looked at energy diagrams before when we were dealing with the Arrhenius equation, right? We know that we have some activation energy that we need, the reaction needs to get over first before the products can even be formed. So there's a minimum barrier that we have to get over, and that's going to be shown by using the Arrhenius equation. So if we pretend we have some kind of reaction, it's going reactants to products, and it's the blue reaction that I have down here. Well, without a catalyst, I'd have to go over this big activation barrier. The bigger the barrier, because we can see that it's actually part of the Arrhenius equation, it's actually going to slow down K. So without a catalyst, the reaction is going to go fairly slow. When you add a catalyst, and this is the high school definition, I'm going to give you a little bit better definition in a second, it quote-unquote lowers the activation energy. I'm going to put that in quotes. Lowers activation energy. It does not actually lower the activation energy. What it's doing is it's taking the reaction through a different pathway. What it usually looks like, and like this is kind of like a simplified one that's on the screen, it usually would go through two distinct steps or more, depends on how many steps are in the catalyzed reaction, where it's the two steps, they're actually completely different reactions going on, but they lead to the same products from the same reactants. It's just a different path, right? And it's using less energy to get there because the catalyst provides a different path. Right? And I think I mentioned this before. I can't remember if it was my 1109 class or my or you guys. It's the idea of summiting a mountain. Right? If you've ever been on top of Mount Washington, right, you can go all the way up to the top and then down the bottom, right? But there's been times when I've hiked it where the weather gets so bad so quick, instead of summiting, you take Lion's Head, which will take you around the summit, and then you can go back down the mountain. That would be like using a catalyst, because we've used a different pathway. Even though I started and ended in the same spot, I didn't necessarily have to go over that more energy-consuming route. And that's what the catalyst does. It's just taking a new route that happens to have lower activation energy. It doesn't directly lower the activation energy of a reaction. Alright, so that's the last slide I have for Chapter 15. So make sure you're checking out the practice problems that are up on EC Learn, and then don't forget we have a small quiz on this stuff, Chapter 15, on Friday. So if you have any questions, shoot me an email, and I'll talk to you guys on Friday.